Welcome to NPTEL course on power system protection. Today we will continue with distance link on lecture on apparent impedance calculation. So, our focus will be on apparent impedance relations for different faults, calculation of apparent impedance. So, last class if you remember, we have this basic configuration of a distance relay having different steps: fault detection, fault classifications. We discuss in detail for the fault classifier, and then this step is apparent impedance calculations, which we will be dealing with today, and the rest is the decision part. So, our focus will be here on today on apparent impedance calculations, which the relay does before checking whether this impedance is inside the characteristics or not for the final decision. So, let us see for different types of fault how the apparent impedance calculation will be related. 3-phase fault balanced. So, we have 3-phase fault. So, let us say this is the 2-bus system. We have a transmission line between M and N buses, and our distance relay is at R m. We know distance relay uses local voltage and current signals. So, we will be using only the signals available at bus M. A fault happens to be there in the line, and the category of fault is 3-phase fault. Let us assume that x corresponds to here the normalized fault distance. So, here x implies 0 to 1 for this line. So, we have two sections from Z M to F and from Z F to N. So, for that corresponding section we have the corresponding impedance happens to be x Z M N and 1 minus x Z M N. Now, for a 3-phase fault, we know at the fault point, this point F point, the 3-phase voltages become 0. So, therefore, VAF equals to VBF equals to VCF equals to 0 voltage. Now, with this relation, we know we can say that for a 3-phase fault, we have we can write down VM equals to IM into this impedance, because this point voltage is 0. So, this voltage becomes equals to Vm, corresponding current in phase A becomes Im, and the corresponding impedance, and similarly Vbm equals to Ibm into this corresponding impedance, and Vcm equals to Icm into this impedance. What you mean by that? That the corresponding voltage here is 0. So, voltage at this point you can say that is nothing but the corresponding current here and the related impedance. The impedance is x Z M N. So, that is what we say for each phase there are the relations are similar. So, therefore, to relate here you can say that the corresponding Poitiers sequence impedance x Z 1 M N from any relation out of these three, we can say V M divided by I M, or V B M divided by I B M, or V C M divided by I C M. Note that for if you go to the impedance corresponds to here, we are talking about a Poitiers sequence impedance, because for the 3-phase fault only Poitiers sequence network remains. So, thus the corresponding impedance from the relay bus to the fault point is x Z 1 M N Poitiers sequence impedance, can be obtained from the relations voltage by current, any phase by corresponding phase current. So, this fault the corresponding Z 1 F or the fault impedance Poitiers sequence fault impedance up to the fault point which the relay calculates can be obtained from the voltage and current of any phases, any phase. So, that therefore, the Z apparent which the relay has to calculate is nothing but this part. So, that can be obtained from V m by M or VBM by IBM or VCM by IBM. So, the relations for apparent impedance which the relay will calculate at bus m becomes VAM by IM or VBM by IBM or VCM by IBM in case of a 3-phase fault. Now, we will go to an example for such a system 230 kV system 120 kilometer line length, and we have the point sequence impedance per kilometer small z 1 0.02 plus j 0.28678 ohm per kilometer. So, this is nothing but from the resistance and the corresponding inductance of the line available to the available. So, therefore, the corresponding total point sequence impedance of the line Z 1 m n capital Z is 120 kilometer into per kilometer impedance. So, that gives us 2.4 plus j 34.41 ohm. Out of this total impedance, a fault is created at 30 kilometers from this 3-phase fault. Now, the fault current recorded at the relay bus are like this 0.79, 0.79, 0.79 each phase, and then we have the corresponding angles for phase A, phase B, phase C. Similarly, phase A, phase B, phase C voltages are having 6.79 much down because of the 3-phase fault close by to the relay bus, and the corresponding angles are there. So, this is a 3-phase balance fault case. So, that is why we are observing similar values for all the 3 phases. Now, the question is calculate the apparent impedance seen by the relay at bus m during this 3-phase fault. So, relay RM obtains these phasors voltage and currents, and now it will calculate the Z apparent. So, from the earlier discussion, the relations we have that Z apparent equals to VA divided by IA or VB divided by IB or VC divided by IC at the relay bus. So, therefore, the corresponding relay we are using VAM by IM corresponding VAM by divided by IAM, and this you can say that ratio gives us 0.6148 plus j 8.6044 ohm. So, this is the apparent impedance which will be calculated by the relay, which will be subsequently will be used for relay decision. The relay will afterwards check whether this impedance is inside the trip boundary or not. If it is inside, it goes for a trip decision, otherwise remains silent. Now, to check whether our calculation is okay or not, I will say that the fault distance means from here to here, the physical distance in terms of kilometer can be obtained from this the corresponding apparent impedance. This apparent impedance is nothing but the point sequence impedance up to the fault point calculated from these available voltages and currents. So, this value divided by the corresponding total impedance, the total impedance divided by this will be nothing but the corresponding the kilometer length of the fault point. So, therefore, we say that you can say that this impedance divided by the per kilometer impedance Z 1 0.02 plus j 0.2868, that gives us you can say that a 30 kilometer length fault point, which is correct because we have simulated the case for the 30 kilometer distance from the relay bus. So, what we say that the fault distance calculated from this you can say that the apparent impedance computed by the relay is in agreement with the actual fault created position. So, that says that you can say that the Z apparent impedance is correctly calculated by the relay. Now, note that the apparent impedance which is seen by the relay, for this fault is smaller than the Z positive sequence impedance of the line Z 1 m n. So, Z 1 m n is 2.4 plus j 34. So, which is much higher than this Z apparent 0.6 plus j 8.6 ohm. So, that implies that this is the relay will go for a decision to trip. We will continue to other types of fault. For the same system, we will now consider for the phase to ground fault, and we will consider for simplicity phase A to ground fault, which you can extend to other faults also like BG type and the CG type. So, phase A to ground fault at F happens to be there. So, we know for such a considered system, the positive sequence, negative sequence and zero sequence networks, they will be connected in series. Here we are for derivations, we are considering RF to be 0, otherwise there should have been a 3 RF here. Now, we see here now the data which will be processed by the relay is only this voltage and current data. So, this is the M bus, so the corresponding currents are positive sequence current and the positive sequence voltage by the seen by the relay, and negative sequence and the corresponding current negative sequence current, and zero sequence voltage and zero sequence current. Now, for this case we know this is a line to ground fault case. So, therefore, phase A, because AG type fault. So, phase A at F point will be grounded, means voltage is 0. So, therefore, we know VAF consists of positive sequence, negative sequence and zero sequence voltages. So, this relation is from the sequence component analysis, VA1F plus VA2F plus VA0F, the corresponding positive, negative and zero sequence components of VAF. So, therefore, this will be also 0. So, this relation is for the A to ground fault, phase A to ground fault. So, from these relations we will proceed further things. Now, from this sequence network we know VAM, we know we consider that the corresponding VAM equals to VA1M plus VA2M plus VA0M, but VA1M we consider is nothing but this voltage VA1F plus you consider this drop VA1F plus this drop. So, VA1F plus I1M x Z1Mn impedance up to this point, positive sequence impedance up to this point. So, this is positive sequence network. So, this voltage is VA1F plus I1 x Z1Mn. So, this is the part we considered about this VA1M. Similarly, for VA2M we have VA2F plus this drop. So, the VA2F plus I2M x Z2Mn, and similarly for the zero sequence VA0F plus this drop. So, VA0F plus I0M x Z0Mn. So, this is what you can say that represented by this representation for the VAM, the fault point voltage at phase A during that time. So, if you see you can say that here we say that I1M plus x Z1Mn, I2M plus x Z2Mn, and the other part here you can say that VA1M plus VA2F plus VA0F, as you have seen, becomes 0. So, they in total becomes 0. So, only remaining first this term and the third term. So, this is this term, this is this term. So, what we have done now that this term is this one. So, we have added now two terms I0M x Z1Mn minus I0M x Z1Mn only for the further analysis. So, we see here these two terms are cancel each out, they are same you can say that term. So, we have added for you can say that further analysis. So, now you can say that from this you can say that you see here that x Z1Mn, x Z2Mn, x Z1Mn, but we know for a transmission system positive sequence impedance equals to negative sequence impedance. So, that is why I can say that we say this becomes also x Z1Mn. So, x Z1Mn becomes a common. So, I1M plus I2M plus I0M. So, these three part gives us this. Now, these two considered parts becomes this minus I0M x Z1Mn plus I0M x Z0Mn. What we will see now that this part IA1M plus I2M plus I0M, as we see in the sequence component analysis, nothing but this IAM. What is IAM? The phase A current at relay RM as seen by the relay RM, and the fault is also phase A fault. So, that is why this part becomes IAM. So, we have x Z1Mn. Now, if you see these two components, so if we take this I0M x Z1Mn common, if you see you can say that I0M x Z1Mn common. So, that becomes equals to you can say that your Z0Mn minus Z1Mn divided by Z1Mn. So, this relates, you can say that if you take I0m x, you can say this. So, that is why I can say this becomes minus. So, this becomes Z0Mn minus Z1Mn divided by Z1Mn. Therefore, we see here that this x Z1Mn Im plus we define a term now K0 I0m x Z1Mn, and then you can say that we see here the corresponding relations where K0 we have defined, you can say that for this term equals to Z0Mn minus Z1Mn divided by Z1Mn. This is called the zero sequence compensation factor, a complex number here, because Z0, Z1 and Z1 are complex number. So, this K0 comes out to be a complex number. We call it zero sequence compensation factor, because we see here in this term, if you see this in this term, we have I0m and that is why Z0, Z1 and Z0. So, that you can say that the corresponding zero sequence has a different terms in terms of, you can say that Z0, and note that Z0 is not same as Z1, unlike Z2 equals to Z1 for transmission line. It is a wide variations, it has can go up to as high as 6 times also from the Z1 depending upon the configurations, which we have already discussed in the initial classes. So, what we learn from here that the VAM is expressed in terms of this relation. So, therefore, from that we can calculate x Z1Mn, which is nothing but the positive sequence impedance up to the fault point equals to this VM divided by Im plus K naught I naught m, and which are, you can say that all the measurements can be obtained by the relay at the local bus M bus, VM measured at phase A, IM measured by at phase A, and K naught you can say that it depends upon the, you can say that line data, and IA naught m you can say that is nothing but we can find IA plus IB plus IC by 3. So, these are, you can say that zero sequence component during the fault situations for this case as seen by the relay RM. So, therefore, we say that the corresponding positive sequence impedance up to the fault point which the relay likes to calculate for the decision, that is what Z apparent equals to VM divided by Im plus K naught I naught m for which category of fault? For phase A to ground fault. Now, if you go to any other category, let us say CG fault, phase switch to G fault, then the corresponding relations will start from this, you can say that VCF equals to 0 and so, and reach you can say that Z apparent equals to VCM divided by ICM plus K naught I naught m or IC naught m same. So, that you can say that gives us the way to relate the corresponding Z apparent in terms of this corresponding faulted phase currents and the zero sequence current. And we found, you can say that another term here the K0, which happens to be the zero sequence compensation factor that is having a complex number. Now, let us see an example for the same system 120 kilometer to 30 kV line, and we have now positive sequence impedance already known, and we require zero sequence impedance for this case. So, per kilometer zero sequence impedance given here, you see here it is higher in the x part and so also the resistance part also compared to positive sequence impedance. The Z1 and positive sequence impedance can be computed in terms of 120 into the positive sequence impedance, and the total zero sequence impedance of the line can be also 120 into this part. Now, let us you can say that see this data which is available for during the fault, and the fault is carried out again at the same point 30 kilometers from the relay bus RM for this 120 kilometer for this 120 kilometer line, and in this case you can say that we see that the IA phase A to ground fault, this is already mentioned, phase A to ground fault case simulated. So, IA is substantially high, IB as compared to IB and IC, VA is substantially down as compared to B and C phases. So, the question is calculate the apparent impedance seen by the relay at RM. So, we know that for phase A to ground fault, we need to consider the zero sequence compensating factor K naught equals to Z0m minus Z1mn divided by Z1mn having a complex number. But note that this Z0mn is nothing but the length of the line into the impedance, Z1 mn is nothing but length of the line into the small z1, that is per kilometer z1. So, therefore, if you see this relation, each one having a length of the line component multiplied to the corresponding per kilometer impedance. So, therefore, the length of the line cancels out and we get a relation in terms of z 0 minus z 1 divided by z 1, where this z small z corresponds to the per kilometer impedance of the line. So, that means that if you substitute, we can consider this value of per kilometer impedance here, then we get the corresponding k 0 to be 1.9310 minus j 0.16668 unit less. Note, if we have, we can say that the total impedance of the line, 0 sequence and negative 0 sequence and positive sequence, you can compute also, or if we have per kilometer length, we can say that per kilometer impedance of the line for the 0 sequence and positive sequence, we can compute from that relation also, because length of the line cancels for this ratio. Now, I will go for the Z apparent using the relations, because this is line to ground fall in phase A. So, V m divided by I m plus k naught I a naught m. So, I naught m is I a plus I b plus I c by 3, and I m you can say that is 0.68 with an angle of minus 150.23 degree kilo ampere. Substitute the value of V a and you can say that this I a and I a naught m, and the k naught is already calculated. So, we got to be considered 0.6024 plus j 8.5947 ohm. So, then you can say that this apparent impedance will be seen by the relay. So, that corresponds to the positive sequence fault impedance up to the fault point. Now, we will check whether the apparent impedance calculated is correct or not. For that, again we will calculate the fault distance as in the earlier example for the 3 phase fault case. So, this impedance whatever is being calculated divided by this positive sequence per kilometer impedance of the line. If we divide that, we are getting 29.98, actually created the fault at 30 kilometer. So, this value is close to that. So, that means that the Z apparent is calculated by the relay is correct, accurate. Furthermore, we can conclude from this data obtained for the Z apparent that this value is much smaller than the Z 1 m n. So, therefore, the fault is inside the line between m and n. So, the relay will go for a steep decision from protection point of view. Now, we will go to the other categories of fault for the same system. So, fault at F, the type is phase to phase fault. Let us consider BC fault, phase B to phase C, short circuit with RF equals to 0. So, for such a situation, we know we can say that the corresponding sequence diagram will be for the phase A, positive sequence diagram, negative sequence diagram, no zero sequence diagram, ground is not involved. So, they are in connected like this, and we see here you can say that V A 1 f equals to V A 2 f at the fault point. So, that is what the relations for the BC fault, V A 1 f equals to V 2 f. So, this relation is obtained from this sequence diagram for this case of BC type fault. Now, we see here the corresponding voltage current relations to obtain the apparent impedance. V A 1 m equals to V A 1 f, this voltage plus this drop. So, this is what this drop, impedance drop. Similarly, in the negative sequence component, V A 2 m at the relay bus will be equals to V A 2 f plus this drop, this one, and the third equation we got V A 1 f equals to V 2 f for this situation of phase B to C type fault. So, if you subtract, you can say that 2 from 1 and use, you can say that these relations for this V A 1 f minus V A 2 f, in that case that cancels out. So, therefore, we got V A 1 m minus V A 2 m equals to I 1 m x Z 1 m minus I 2 m x Z 2 m n. So, Z 2 m n equals to Z 1 m n for transmission line. So, that we got x Z 1 m n common I A 1 m minus I 2 m. So, therefore, you can say that the x Z 1 m n, the positive sequence impedance up to the fault point from the relay equals to V A 1 m minus V A 2 m divided by I A 1 m minus I A to M. The positive sequence voltage minus negative sequence voltage divided by the positive sequence current minus negative sequence current at the relay bus. From the same diagram which we earlier seen, we will continue. You can see that how we can represent the corresponding sequence voltages and current for the in terms of the phase voltages and currents. We know that the corresponding phase voltage V B M can be expressed in terms of the positive sequence voltage and negative sequence voltage and zero sequence voltage, and this is what the expressions we know from the sequence component. And then we know for this phase C also you can say that this is a BC fault, the corresponding relations becomes alpha V A 1 m plus alpha square V A 2 m plus V A naught m. So, this is the general expressions for phase B and phase C. So, if we subtract V B m minus V C m, we got V A 1 m alpha square minus alpha, V A 2 m alpha minus alpha square. So, V A 1 m minus V A 2 m alpha square minus alpha. So, V A 1 minus m minus V A 2 m becomes equals to V B m minus V C m divided by alpha square minus alpha, that is one relations. Similarly, I B m minus I C m on the current relations from the general relations for the sequence component, we can compute I 1 minus I 1 minus I 2 m minus alpha square minus alpha, and from here you can relate I 1 m minus I 2 m equals to I B m minus I C m divided by alpha square minus alpha. So, x z 1 m and the fault impedance up to the fault point from the relay bus, which we have already derived V 1 m minus V 2 m minus I 1 m minus I 2 m in the last slide. So, that becomes equal to from these two relations of voltage and currents, we can express V B m minus V C m divided by I B m minus I C m. So, what we say that the fault impedance up to the fault point from the relay bus can be obtained from the phase voltage difference and upon current subtraction. So, we see here for the BC fault, the general expression for the Z apparent, because this corresponds to our Z apparent here as required by the relay, positive sequence impedance of the fault point can be obtained from the measurements by the relay for phase B voltage minus phase C voltage upon phase B current minus phase C current. Note the fault type is BC fault. So, we are using B and C voltages and current for the expression for the Z apparent. So, if you go for any other category job in a similar way, like let us say AB fault, for AB fault the corresponding Z apparent will be equals to at that time V A minus V B upon I A minus I B, and for CA fault we will be having B C minus B A upon I C minus I A at the measurement bus by the relay. So, this gives us, you can see that for the phase to phase fault the corresponding Z apparent expression. So, we found that for 3 phase fault it is V A divided by I A kind of thing, and for line to ground fault AG fault we got V A divided by I A plus K naught I naught, and for you can say that BC fault we got, you can say that Z apparent equals to V B minus B C divided by I B minus I C kind of thing. Now, we will see the fourth category, the last one, that let us say the fault is BCG type in the same system at F, and in this case the sequence diagram becomes 3 parallel things networks, positive, negative and 0. So, we know this, and our measurement bus is at M position as positioned by the relay. So, we see here that for this case again the positive sequence and negative sequence are in parallel, agree. So, therefore, we know that this voltage V A 1 F equals to again V A 2 F. So, this we saw in the phase B to phase C also in earlier phase to phase fault also same relation, and this was our starting relations. Now, if you see this relation also here also V A 1 M equals to V A 1 F plus this drop, and V A 2 M equals to V A 2 F plus this drop. So, these three relations are same relations what we saw for the phase B to phase C fault also. So, therefore, you can conclude that for this kind of fault also BCG type fault also the final relations for the apparent impedance will be V B M minus V C M divided by I B M minus L C M. That we mean that the type of fault BC and BCG, they have the same apparent impedance relation of VB minus BC upon IB minus IC, and similar also you can conclude for CAG fault or ABG fault for the apparent impedance calculation. Now, let us see an example now. An ABG fault, same point 30 kilometers, and the corresponding fault data are provided here and voltages are also provided here. So, fault is in AB. So, that is why the voltage in A and B gone down and currents are up. Now, we will find the consider the calculate the apparent impedance for this case as seen by the relay. So, data for the line are provided as we have seen earlier. Z apparent equals to, this is a AB fault. So, corresponding voltage V A minus V B upon I A minus I B relation. So, you substitute the data and then got the corresponding apparent impedance to be 0.6158 plus j 8.6032 ohm. So, we can check, we can say that what is the fault distance here. So, this impedance upon the per kilometer impedance of the positive sequence impedance. So, that divide we got this corresponding kilometer to be 30.01. So, we created fault at 30 kilometer and we found this distance to be a similar length. So, that means that Z apparent seen by the relay is correct, accurate. Furthermore, we see that this impedance Z apparent is smaller than Z1 Mn, which is having 2.4 plus j 34.41 ohm. So, therefore, the relay will find this fault inside the line and go for a trip decision. So, in summary, with that for the different kinds of fault, we can say that 3 phase fault Z apparent equals to VM upon IM or VBM upon IBM or VCM upon ICM. Phase to ground fault AG, PG or CG, we know for the Z apparent equals to VA upon IA plus K naught IA, VB upon IB plus K naught IA naught, and or VC upon IC plus K naught for the CG type of fault. And for phase to phase fault or phase to ground fault AB ABG, BC BCG and CA CG, the Z apparent becomes equals to for AB and ABG BA minus BB divided by I minus IB, and for BC and BCG correspondingly BB minus BC divided by IB minus IC, and for CA CAG BC minus BA upon IC minus IA. So, this is our the corresponding how the relay will calculate the Z apparent for different types of faults. What we found from this that the relation for you can say that different types of fault, the corresponding calculation of Z apparent is different. It means that the relay needs a fault classifier, which we have already seen the our module of the distance relay, fault classification, subsequently for apparent impedance calculation. So, this reveals that to consider we require a fault classifier to accomplish the apparent impedance calculation. Now, we will see a practical field data in India grid. So, a 132 kV transmission system having 73 kilometer length 50 R system. So, we have positive sequence parameter, zero sequence parameter per kilometer given here. We can find the Z1 Mn, the total impedance of the positive sequence impedance of the line 1.752 plus j 19.27 ohm. For the situation, fault data are available, the relay recordings provides. So, the fault current at RM is IA having 967.4 with an angle of 5.8 degree, IB having 92 point this and IC having 68.9 ampere, VA 5.8 pretty small, BB and BC are having 73.76 or so. So, this if you see this fault data, then it reveals that it is a very likely phase A to ground fault, but the relay has to decide based on the data. So, Now, for the apparent impedance calculation and subsequently for the relay decision, before apparent impedance calculation, the relay has to know that which type of fault it is. Accordingly, the corresponding voltage current relations will be used. So, we use the current based fault classifier already learned in earlier lectures. So, we compute the corresponding I A 1, I A 2 and I 0 and then compute the delta 1, delta I positive and delta I 0. So, delta I positive is nothing but I A angle of I A 2 minus you can say that angle of I A 1 and delta I 0 is angle of I A 2 minus angle of I 0. Using these two, we find that it positions in this A g and here also it ensures that this is in A g and we see that zero sequence component is significant, all are almost of similar order. So, that ensures that this is a phase A to ground fault. So, this ensures of phase A to ground fault, now we will activate the corresponding apparent impedance calculation. So, this means that A g fault. So, we know that the corresponding voltage and currents will be used for that V A upon I A plus K naught I naught. So, for that we require K naught. So, K naught can be obtained from the data from here. So, we got to consider this to be a 2.178 minus j 0.08 is sequence compensating factor. Z apparent equals to V A upon I A plus K naught I naught. So, substituting the V A, we got this to be 1.21 plus j 3.32 ohm. Note that this Z apparent impedance is much smaller than the positive sequence impedance of the line. That means that the fault is inside the line, the relay will go for a trip decision. So, in summary, Z apparent calculation is integral part of this distance relay. It uses the local currents and voltage for this. For that, the corresponding relation, proper relation of Z apparent, we require a fault classification, fault type must be known. In case of phase to ground fault, zero sequence compensating factor is being used only for phase to ground fault, not for any other types of fault. K 0 happens to be complex also and depends upon the line parameters. Now, the last question comes to is that is Z apparent equals to V by I? Not, because in case of we are not that V A divided by I A or so. For phase to phase faults, it is B B minus B C upon I B minus I C relation, and particularly for phase to ground fault, it is V A upon I A plus K naught I naught kind of relations. So, therefore, it is not simple as phase voltage by phase current for Z apparent calculation. So, we saw that you can say that how the Z apparent can be calculated by relay successfully. Thank you.